Welcome back to ECE 220. We're essentially, after today, halfway through the semester, pretty much. We've finished 2 exams. You have 2 more midterms and a final. And you have more of your labs due than what well, I guess if you count the lab 0, we've basically completed, or you will be completing half of your labs essentially with 0, 1, and 2. But you're still reading chapter 6. We've been talking about, or these inductors have been taking selfies. Now we're going to be including more in the picture. We're going to be doing mutual inductance so that we have to worry about dots. So you might look at the last part of chapter 6 dealing with mutual inductance, where we now have to not only worry about one coil, the self inductance, but we also have to worry about coupled coils and mutual inductance, and we'll introduce dot notation next week or Monday when we start talking about mutual inductance. Today we want to finish up with capacitors. Saturday, I know you've all been clamoring to deposit your pre-lab into the assignment drop box. I think you can do that now. It wasn't available until yesterday, but if you're now needing to submit that, I think you can. I don't know if anyone's tried yet, but it should be open. That's to get you ready for lab number 3. That's group A. That's most of the sections. Homework 8 is due next week, and that's dealing with capacitors and inductors. Homework 9 will be dealing with mutual inductance, and that will then be giving us the information that we need for exam number 3, op amps and chapter 6. So chapter 5 and chapter 6 will be exam number 3, and Group B, your lab report is due for lab number 2 next Wednesday, and then you have to follow that up pretty quickly with your pre-lab next Saturday. I know you've been dealing with KVL and node voltage analysis, mesh current analysis. We need to get back into chapter 6, which is capacitors or ICE. We'll just remind ourselves of what we're dealing with based on the acronym ICE. We'll go through an example of actually finding sort of the opposite from what ICE might nicely want us to do. Instead of differentiating voltage, let's integrate current to try to find the voltage across a capacitor. We'll look at expressions and examples, or one example for power and energy in an ideal capacitor. We'll see how capacitors combine. They will now be the dual of what we've been seeing with resistors and inductors in terms of the formulas or the expressions. And then we'll see if we have time for some review questions. To review, ICE means we can say what? ICE is there to remind us of the current voltage relationship of a capacitor. I've given you the I part. Now what's on the other side of the equality sign? If now we're interested in the current voltage relationship of a capacitor, I is equal to C dV dt. So that's now what we know to be true for a capacitor. And if you invert that, essentially, or try to find voltage from current, then you can do that with this second row expression, which is now saying that the voltage across a capacitor at the present time is what the voltage was initially, whatever the initial was, that's our T sub 0, plus the second component, which uses the current from t sub 0 to t. So maybe I should say this uses the current from t sub 0 to t in order to compute the second component of that voltage. If you don't have any initial voltage or no initial condition on your capacitor, you'll get all of your voltage on that capacitor due to the integral or integrating current. Let's now work through an example to try to drive home that relationship between current and voltage on a capacitor. Suppose we're given the following. We're given this information shown. We are told that the initial voltage on the capacitor is 0. We're told the capacitor is 1 microfarad, and somebody now tells us that this is the current waveform associated with that capacitor. They're essentially telling us that it's linear from 0 to 1, and the time axis is in seconds. Let's label that. So this is now in seconds. And then from 1 to 2, the current actually changes sign, but now it increases again in this linear fashion from 1 to 2, and it's maybe I want to label this a little differently. I'm kind of doubling up too many things. So let's just say that's in amps, so that now we're going up to 4 times 10 to the minus 3. That's 4 milliamps that we're going to. So I guess my axis was okay. Yeah. Do you see where I'm struggling with my units? I could say that's 4t, but I really want that to be expressed in amps. So this is now 0.004, but I really wanted to just use 4 on my axis label. So this is in milliamps, and this will be minus 4 milliamps. So I of t is in amps, and we're going up to 4 times 10 to the minus 3, so that I can now just say I'm going up to 4, but that's now scaled by 10 to the minus 3. We okay with that? And the increasing current from minus 4 milliamps is linear, but it's starting now at time 1. It's actually at minus 4 times 10 to the minus 3, and then at 2 it's done. So I think our functional expressions for this current waveform are okay. Let's now find V of t, knowing what we know from ICE. ICE tells us that we now have C dV sub C dt. That's what current is, but now we're given current, so we actually need to find voltage from current. And we can do that by breaking that up into 2 pieces, the initial voltage and then our second component dealing with the current from the initial time up to now. And what's that going to be? We can divide both sides of the ICE equation by C and then integrate both sides, and we end up then going from t sub 0 to t of I sub c of tau d tau. Now, if we do that since our current is now changing functionally over this 2-second interval. The first second it has one functional form, and the second 1 unit interval or 1 second interval, it's different between 1 and 2. Let's now find the voltage over those 2 different segments of time. Now we're looking at from 0 to 1. what's the integral expression going to look like? What are my limits on the integral? And now I want t to actually be variable. I want to know if somebody says, oh, what's the voltage at time 1/2? I want to be able to plug t equal to 1/2 into this v sub c of t expression. And that's then influencing what I label or use as my limits on the integral. Where am I starting? What's the lower limit on the integral? 0. That sort of was given away by that. Those should be the same. That's t sub 0. What's the upper limit? So now I'm wanting this functional expression of voltage to be true between 0 and 1, but I want it to be true at each point t in time between 0 and 2. I want to find it. So if I wanted to find the voltage at time 1/4, I would integrate from 0 to 1/4. If I wanted it from 1/2, I would go from 0 to 1/2. I want that upper limit to be variable so that I can just plug in the t value, which now means that my upper limit, I'm just going to call t. That's what v sub c of t will need in order to find the correct functional form. And in here it's I during that interval from 0 to t, and now I'm just focused on that from 0 to 1, so I can keep the same functional form. This is 4 times 10 to the minus 3, and that was sloping with slope t. Here my variable of integration I'll just call tau d tau. We were given that the initial voltage was 0. That now goes away. We were told what the initial capacitor voltage was. V sub c of t is now 1 over the capacitor, and the capacitor was 1 microfarad, I think. Is that what it was? Yes, it was 1 microfarad. C is now 10 to the minus 6. We integrate that from 0 to t. Or let's just go ahead and do the integral. We now have that constant, and we need to integrate t dt, or tau d tau, or x dx. And that's our 1/2 tau squared, and we then evaluate that at the upper limit and then the lower limit. The 4 and the 2 combine to give us 2. The 10 to the minus 3 plus 10 to the 6. When we put that 10 to the minus 6 upstairs, we have now 2,000 t squared. And that's volts, which is true between 0 and 1. That's now the functional form of our voltage. Our current was linear. Our voltage is now quadratic. It's this rounded shape now from 0 to 1, more rounded. And we can now evaluate what the voltage would be at 1 by substituting 1 into this equation. Or now we know we're at 2,000 volts at time t equal 1. And that's important, because now we need to use that to try to find what's happening to our voltage for the next interval of time from 1 to 2. Now we're trying to find the voltage across that capacitor from 1 to 2. We break that determination of voltage into 2 parts. The initial condition, which in this case, what's in the argument for the first term? What's V sub C of parentheses blank? What's in the blank? Is it really that much? Okay, good. I'm seeing some fingers. Well, the correct answer, right, was 1. So that's the initial condition, V sub C at time 1. And how do I now write my integral? What are my limits? 0 to t. So now it's 1 to t. And the functional form is different now for the current. This is 4 times 10 to the minus 3. This was t minus 2. This now, in terms of variables of integration, tau minus 2 d tau. We now are starting that voltage at 2000, and we need to now evaluate the integral. This is now 1 over 10 to the minus 6, integral from 1 to t, 4 times 10 to the minus 3, giving myself time to remember how I'm going to integrate this, but that's just going to, we can distribute that integral across the two terms and just integrate a tau and a constant. Or we now have 2000 plus, now the 10 to the minus 6 downstairs combined with the 10 to the minus 3 and the 1/2 that comes out from integrating tau and the 4 gives us 2000 tau squared from the lower limit to the upper limit. And then if we multiply 4 times 2, we get 8. Combine the exponents, we now have 8,000 coming in with a minus sign, tau from 1 to t. That's just separating that integral into the two pieces. Since the integration operation is a linear operation, that's allowed. We now have this expression, which we can evaluate at the upper and lower limits, or we now have 2000 plus 2000 t squared minus 1 minus 8,000 t minus 1. Make sure I'm doing my algebra right. I now can combine all of these. I only have one t squared term, and that's the 2000. I only see one linear term in time, and that's minus 8,000. And then I have to keep track of all of the constants. I have 2000. I have minus 2,000. Those cancel, and then I'm just left with the minus, a minus 8,000 or a plus 8,000. That's now my functional form for V sub c of t for t between 1 and 2. And if somebody now wants to know, well, what's my voltage right at time 2? We simply evaluate that at 2, and we now end up with 2,000 times 4 minus 8,000 times 2 plus 8,000. We have 8,000 on either side of minus 16,000. That now conveniently cancels, and we're at 0 volts. Or for all time thereafter, since the current is nothing and integrating nothing gives us nothing, we know that our voltage across that capacitor is 0 for all values of time greater than 2. And if we wanted to sketch that, what was it between 0 and 1 functionally? That was now 2000 t squared. That's this parabola we can try to sketch. This now goes up, and this is now 2000 volts. And then at 1, we know it was at 2000, and then between then and 2, it goes to 0. It does that with this quadratic, and it's now going to look like that. What's happening between 1 and 2? What if you said, oh, this is the voltage across that capacitor? It's now building up. What are we doing to the capacitor? And now I'm looking for charge or discharge. We're charging the capacitor here. And it's then giving back that charge in the second time interval, or it's now discharging. And that was determined by applying this current wave shape from 0 to 2. We now charge up the capacitor, discharge it, and that's now shown in this voltage sketch. And it charges up non-linearly as a square relationship. That's now current and voltage. Let's now combine those and worry about power and energy. Power is now just the product of current and voltage. We've now learned how to relate current and voltage with respect to capacitor. Ice, you're going to, well, I'm doing this for a reason. Hopefully now whenever you wake up and somebody says ice or Eli, you can just recall I equals C dV dt, or V is equal to L di dt. Until you retire. I was talking to a former dean last Friday, wow, a week ago, and he was talking about Maxwell's equations. And I go, wow, you remember those? He said, well, I might have to rederive them. So I was impressed. But I said, well, I usually tell the students they need to remember a few things from now until when they retire. And I've had students that say, well, I'm retiring in 5 years. I said, okay, you don't have to remember it for very long. That's fine. But this is one of those. If somebody now says, what's the current voltage relationship of a capacitor? Even though you may forget most everything else, you could derive a lot from this. And what is that? I sub C, that's the I part. The C is just the capacitance of this device. And E is electromotive force or voltage. And now we have I is equal to C dV dt. Power is the product of I and V, or V and I. V, let's just leave alone. I sub C, let's replace that with this voltage expression, and then combining that, pulling the C out in front, we have C, V sub C of t, dV sub C of t, dt. And that might be helpful when we want to integrate power. Now it's just in terms of this one variable voltage. And if we now integrate power over time, we can now say that that's, here we're assuming the capacitance is constant from minus infinity to infinity of V sub C of tau dV sub c. The d lambda was d time, and we canceled the dt underneath the dv sub c. Now we have this integral of x dx, that's 1/2 x squared. We now see that the energy of a capacitor is dual to what we saw the energy was in an inductor. The inductor was 1/2 L I squared. The capacitor is 1/2 C V sub C squared. And now that we have all of those formulas, let's use them. And the book walks us through a nice example. If you want to now look at better figures than what I'm going to draw, you'll probably draw figures better than what you see in the textbook. But if you now look at example 6.4 in the textbook, we're going to now look at an example that uses these concepts. We know the current voltage relationship, that's ICE. We know power is voltage times current, and energy in joules we can find if we know the voltage. That's just 1/2 C voltage squared at a given time. In this problem, we're told that we have a 0.5 microfarad capacitor. That's the capacitance. And then we're given, again, another voltage waveform that is functionally different in 3 different time intervals. We have a time interval from -infinity up to 0, where it's nothing. Our voltage is then 0 before 0. Between 0 and 1, and the units on this will be volts. I don't know how close to make that. I don't want you to confuse that as being a variable for the 4t. The functional form for the voltage is 4t, and that's in volts. We're now going to go up to 4 in a linear fashion. And then we're going to go down exponentially. Where are we going to start that exponential? What's the value of that third waveform expression at time t equal to 1? The exponent, the time, has now been shifted by 1, so this is now an e to the minus t, but shifted over to be starting essentially at time t equal to 1. Now the exponential decay is e to the minus t in shape. It starts at 4, and now we go down exponentially. And at 2 units of time, where would we be relative to where we started? If you just had to put some dots in there to make your sketch a little more accurate, how would you put it? Where would you put that dot at time 2? Where would it be numerically? What would the value of this? And my sketch is probably not very well drawn. What would that dot be numerically? So it's now 4e to the what? Minus the quantity 2 minus 1, so it's e to the minus 1. 1 over e. 1 over 2.7. Or what is that? Isn't that about 37%? So you could have said, oh, I'm 37% of where I started, about 0.37. So now I would just be 37% of 4. This is now e to the minus 1. Just to give you a way to think about where you're at. That's our voltage waveform. What's our current? Our current will also have 3 unique functional forms. The first one, I'll do that. That's the hard one. Before time 0, I of t is 0. Since I know ice, I is equal to C dV dt. The voltage is not changing before 0. I don't have any current associated with that capacitor. And it's now going to be flat. What's the second piece going to be? Between 0 and 1. Is it 4? I differentiated current. Isn't that what? I'm sorry, I differentiated voltage. I is equal to C dV dt. But we can't forget C, can we? We need to scale that by the capacitance, which was 0.5 microns. Or this is now 2 microamps from 0 up to 1. It is flat. It's C dV dt, but there they gave us a nice functional expression for V. It was 4t. I can still remember how to differentiate 4t. I just get 4. I now have C times 4. That's now giving me 2 microamps, and it's constant. We have a constant current flowing through that capacitor. And this is the conduction current at the terminals. What's the second piece? Well, now this is why you went through all this calculus, is so you know how to differentiate different waveforms. This is now an exponential, or we now have this is going to, again, it's going to be scaled by the C, so I don't want to forget that. And then I differentiate that. And above 1, I'm now going to be at this minus 2 e to the minus t minus 1 functional form. And that's in microamps. Meaning I've now flipped sign. I've now gone down. Maybe I shouldn't even draw that. And I'm exponentially decaying from the minus 2. That's now what's happened when I essentially start decreasing the voltage, and I started decreasing the voltage exponentially. Now my current changes sign. I'm now giving back things, or having charge go in the other direction. That's now my current and voltage waveforms. We were given the voltage, now we've sketched the current. What about the power? Well, we can remember that that's simply I times V, or V times I, and we have both of those. We can just multiply them together. 0 times 0, it's going to be 0 for time less than 0. Between 0 and 1, I have 4t times 2 micro. And what are my units? This is now power, this is now microwatts, and that's between 0 and 1. For time bigger than 1, I now need to multiply the 4e to the minus quantity t minus 1 times a minus 2e to the minus quantity t minus 1. Those exponents add. I end up now with e to the minus 2 times the quantity t minus 1. And I now have minus 2 times times 4 to give me minus 8. E to the minus 2 t minus 1, and that's for time bigger than 1. And the units are microwatts. If I now wanted to try to sketch that, I'm going to now go up to 8 linearly. This is now P sub c of t, and this is in microwatts. This is now my value of 8. And then what happens at 1? Now I've changed signs. Now I was absorbing power into my electric field of the capacitor. Now I'm going to be discharging. And that means I'm going to be delivering power back to the rest of the circuit, and this one's going to be functionally a little different. It's now going to be falling off at a faster exponential rate. I'm not sure that my sketch is accurate enough, but it should be decreasing now at e to the minus 2t instead of what the voltage or in the current were, which were e to the minus 1t's. Here we are absorbing power. And in this segment of time, we are delivering power from our capacitor to the rest of the circuit. And then we can do our energy. And what's energy? Instead of worrying about trying to integrate power, let's just use 1/2 c v sub c squared. We have the v sub c. Let's just use that expression. This is now 1/2 c v sub c squared of t. We can go back to our original v sub c and square that, keeping the c involved. We have 0 for the first segment. We have 1/2 c, which was 0.5 microns, times v squared. Here it was 4t. We square that, it's now 16t squared. And this is now in microjoules. If you combine all of those, you have 1/2 times 1/2, which is 1/4 times 16. This actually ends up being 4t squared microjoules between 0 and 1. And the last one is again 1/2 c times the voltage squared, but that's now just 16 e to the minus 2 times the quantity t minus 1, squaring that exponential term. Or these constants now combine like they did before, and our expression, or the waveform, now if I keep my 1 in the same location, it's now going up as t squared, and it gets to 4 microjoules. That's now this parabola shape, this quadratic, and beyond 1, it's now an exponential shape starting at 4, but now it's exponential with an e to the minus 2t. So that diagram, or that waveform, should be a little non-symmetric. Should be non-symmetric relative to 1. The one side is a square shape, the other is an exponential. And here, what's happening? Now the capacitor is storing energy. And from here all the way up to time forever, the capacitor is now delivering or returning the energy that it had stored to the rest of the circuit. And hopefully you're not a part of that circuit when it returns its energy. That could be painful. That's why when you open up something, electronics, it always says, whoa, wait a minute, be careful, because what? Those capacitors could be storing things for more time than what you just turned the on-off switch. So there may be some energy hiding there ready to escape and greet you, maybe not so in such a friendly manner. You might get a pop. Let's now combine these capacitors. Parallel combinations. We're starting with that because that's the more straightforward. This is now the dual. These are going to have dual functional expressions versus what happened with the inductors and resistors. ICE now tells us that we have I sub c of t is equal to c dv sub c dt. And we know how to apply KCL. KCL says the total current in our equivalent single capacitor circuit is really going to be functionally the same as those 3 currents going down. And we know Eli can be applied in all of those terms. Now we have C1 dVc dt plus C sub 2 dVc dt plus C sub 3. And the voltage, those are all in parallel. They all see the same voltage, which now allows us to factor that out. Which says that now if you're combining capacitors in parallel, now they add. The equivalent capacitor for a combination of many different capacitors in parallel, now you just add up those capacitor values, the capacitance. That's what happens when you have capacitors in parallel. The dual to what resistors were looking like. This is how we combine resistors and inductors in series. That's the dual nature. What about the series? Now what you have to convince yourself of is that the charge on each of these plates, the positive plate and the negative plate, on all of those capacitors are the same. You're displacing the same amount of capacitor or charge on C1's plates, C2's plates, and C3's plates. Now I'm hungry. I've been saying plates so many times. But we now have capacitor conductive. Trying not to say plate. Anyway, we have plates that are separated by this dielectric. We're combining them in series. They share the same current. I sub C is the same, and the charge actually is the same. And we know that the charge-voltage relationship of a capacitor is Q is equal to CV. That's where we get that's where we get ice. We could differentiate that. If the capacitance is constant, we could say dQ dt is equal to C dV dt. And dQ dt is the current. So if you forget ice, maybe you can remember this. Q is equal to CV, or V is now Q over C. We tried to show in this illustration that the charge on each of the positive plates in C1, C2, C3 is the same as the charge on the equivalent capacitor plate. Likewise for the negative plate, so that if we now do a KVL, essentially, we would say, oh, we want the equivalent on the right. That voltage needs to be equivalent to V1, V2, V3. We now know that V equivalent is V1, V2, V3, but we have this relationship for voltage. And so now we have Q is the same in all these cases. Or we can now factor out that equal Q. Cancel it, and we see that now in series, these capacitors combine in their reciprocals. You add reciprocals to get the equivalent reciprocal capacitance. 1 over C equivalent is now 1 over C plus 1 over C2. And you know what a pair of capacitors, how they would combine. You would now, in series, it would be C1 times C2 over C1 plus C2. And that's what you'll need to remember on your homework and on the exams, is how to combine inductors and capacitors in the various series parallel combinations. Let's do an exercise. Now that we're at the end, we forgot to stretch maybe at the first of class. Let's do our stretching now after we've worked out, maybe, so we're not quite as sore this afternoon. I know if you don't do your electrical engineering every so often, you'll get sore. So here's the first exercise. We have an inductor governed by Eli, and we're told the current. I is equal to 7t e to the minus 3t, and we want to know what's the energy stored in that inductor at time 50 milliseconds. What's that I of t waveform look like? T e to the minus t. Can you see that? Can you see t? If I say what's t, you know you're sloping. If I say e to the minus t, you know you're exponential. Now we're combining those with a product. What's t e to the minus t? Are we going up? Are we going down? What's t e to the minus t? What's that look like? I want you to be comfortable with what that is waveform shape-wise. What is t e to the minus? Here it's t e to the minus 3t, and it's scaled by 7. Well, we could say, well, what's going to dominate for small values of t? What's e to the 0? What's anything raised to the 0 power? 1. What's t at 0? 0. So now e to the minus, when t is small, is not going to be as influential as the t term. So this is really, in a sense, this is going up and then it comes down. So that's what this t e to the minus t shape looks like. We're now applying that pulse of current into this inductor, and somebody wants to know what's the stored energy in that inductor at time equal 50 milliseconds. You can just plug in your equation. You know the energy is 1/2 L I squared. You can find I at time 50 milliseconds, square it, and scale by 1/2 L to find the energy at 50 milliseconds. We'll pick up with selfies and mutual inductance next week.